Materials have another important property, and that is conductivity. For that, we use the symbol sigma, and it has units of Siemens per meter. And if you don't remember, those are 1/ohms. And sometimes people even use the symbol of an upside down omega, or they will write it as mhos, which is ohm backwards. Anyway, conductivity. And it relates a volume current density, J, to an electric field, E. Remember, electric field is volts per meter, so you end up with amps per meter squared in the volume current density, which is what you should have. So, the conductivity of a material is determined by the volume density of charges that can move times the mobility of the charges. And the mobility of charges gives you meters per second per amount of electric field applied, so that's in volts per meter. So the units of that are kind of weird. But it is how fast do the charges move in response to an electric field being applied to this thing. And this is just how many charges are there. Knowing that, let's talk about how we get from the volume conductivity of something to something that we're more familiar with, like resistance. Let's think about a cylinder. We have a cylinder here, and it's filled with a material of some conductivity sigma, and it has an applied electric field. Let's make it E. And let's say for ease of operation, this electric field is constant inside. And it has some height, and it has some area A. In fact, instead of an area, I'm going to give it a radius, little a. The current flowing through the cylinder is equal to the surface integral of the volume current density flowing through a surface, its cross-sectional area. So in this case, that would be that circular end cap. So we could take the current density through there or through some slice in the middle. Substituting in what we know, that the volume current density is equal to the conductivity times the electric field, dot dA. Since the electric field is constant inside the cylinder, we end up with sigma pi little a squared times the magnitude of that electric field. Because the electric field is co-directed with the surface normal vector. So that's the current. Okay, what's the voltage? From how we've defined the voltage, we have minus the integral from one end of the cylinder to the other end of the cylinder. We'll have it be plus to minus like that. So the integral is generally done from the minus end to the plus end. And it will be E dot dl. Electric field is pointing up. dl is going to be pointing down. So that ends up being minus magnitude of the electric field times the height, or magnitude E times H. So if we want to talk about the resistance of this cylinder, the resistance is just the voltage divided by the current. But we have both of these in terms of the electric field now. So that's magnitude E H, which we computed with this line integral, divided by pi a squared magnitude E sigma. Canceling out stuff, we have that it's H over pi a squared sigma. And in general, you will find that increasing the length of a resistor increases its resistance, while increasing its cross-sectional area decreases its resistance. And so does increasing its conductivity. This formula depends on the assumption that the electric field is constant inside the cylinder. If the electric field is not constant inside the cylinder, instead of purely having the length or the cross-sectional area of your shape, you might end up with sort of a weighted average of the electric field, or some function of how the electric field is shaped that modifies the conductivity. But it's still going to be some function of the geometry and a factor of 1 over the conductivity.